Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to find the center of mass for a composite body. So what we're going to do here, we're looking at this system right here with the following dimensions here. We've got this 5-foot piece and it's 21 feet long, 6.5 feet high, and 5 foot across the top here. And what we're going to do is we're going to try to calculate the center of mass x bar y bar for this geometry, assuming that it's a nice uniform piece of geometry, meaning that the density is the same along here and vertically. It's all made of the same material and it's the same thickness. Now, if it's made of the same material and the same thickness, we can actually find the center of mass by finding what's called the center of area. So what we're going to do here is we're going to do if you've seen my videos about centroids and center of mass, center of area, we're going to use the idea of weighted average to try to calculate the centroid of this geometry. Now, before I even do that, what I'm going to do is I'm going to break this up into pieces. All right, so I'm going to just draw myself a vertical line right here, and I'm going to, probably do a little better than that. Vertical line right here. I'm going to call this piece 1. I'm going to take this, draw another vertical line right here, call this piece 2, and this piece 3. So what I've done here is I've broken this thing up into 3 chunks. This chunk is going to be a triangle, and then we're going to deal with a rectangle, and then a triangle again. And what I'm going to do is I'm going to take the x and y coordinates of each piece and average them by area. Now, when you're dealing with these composite bodies, I find it's probably best to kind of deal with this stuff in tabulated form here. So what I'm going to do here is I'm going to put chunk 1, chunk 2, chunk 3. And what I'm going to do is fill out a table here. I'm going to calculate x bar for each chunk, y bar for each chunk. We're going to need the area of each chunk. I'll go ahead and calculate that, and we're going to use these values to calculate the centroid of the entire geometry. So starting with piece 1, x bar and y bar. So here's piece 1, and this is a triangle here. So the centroid of piece 1 is something about like this. Now remember, if you've seen my video about centroids here, 2/3 from the corner or 1/3 this way doesn't really matter. So let's say 2/3 times 5 here. So x bar is going to be 2/3 times 5. I'm just going to go ahead and erase that and put 10/3. Which is, I guess, let's use 3.33, and these are all going to be in feet. Okay, y bar is going to be 1/3 up in this direction from the corner, so that's going to be 1/3 of 6.5, which is 2.17 feet. The area for chunk 1, let's see, this is a rectangle, so it's area, and I'm going to do this off to the side and just put the results right here. So the area for chunk 1, 1/2 base times height. And I get 16.25 feet. I'm sorry, 16.25 square feet. So I'm just going to put these guys are going to be in feet. These are going to be in square feet, so I don't have to keep writing the units. All right, now let's deal with chunk 2 here. So this thing right here is a rectangle, so its centroid is going to be in its geometric center. This distance is going to be 2.5 feet, half of this distance. So we're going to be 5 plus another 2.5, or in other words, 7.5 feet for x bar for the rectangle. Okay, now the y bar for the rectangle, that's this height. That's going to be half of the 6.5, so it's going to be 3.25 feet. And then the area is the product of the two, 7.5 times 3.25, 24.38, let's say 24.4 feet, square feet, 24.4 square feet. Chunk 3. So chunk 3 here, we're looking at another rectangle, so its centroid is, something like maybe this, 1/3 away from the corner, or 2/3 from the end. Now, let's see, so this entire distance right here is going to be, let's see, 21 minus 5 minus another 5. That's 11. So this distance is going to be 1/3 of 11, which is 3.7 feet. Write that so that we can read it. And again, those are in feet. And then 1/3 of this dimension, that's going to be 1/3 of 6.5. 2.17 feet. And then the area of this guy, so this is going to be a triangle. So the area of this triangle right here, I'm going to write this down over to the side here, is going to be 1/2. Its height is 6.5 feet. And this dimension was, I forgot it, but let's see, 21 minus 5 minus 5 more, 11 feet. And that product calculate x bar for the entire geometry by taking a weighted average. We're going to average all the, I'll say x sub i's here. I'll put this over to the right. We're going to multiply that by a sub I, meaning the area of the I, like the first, second, third geometry. We're going to sum those all up. Then we're going to divide by the total area, or the sum of all the a sub i's. So if I write out what that's equal to, so for geometry 1, that's going to be 3.33 feet times the area, 16.25 square feet, plus, okay, and I can see right now that I'm going to need more room here. So what I'm going to do, take this entire thing, shrink this down a little bit, lift this up. I'm going to restart this calculation down lower because I want to try to get this into one line. So I'll write this all out right here. All right. So this was x bar for rectangle 1 times its area, plus x bar for the second geometry, 7.5 feet, times the area, 24.4 square feet, plus x bar for the third geometry. Whoops. And some of you probably already had thought this was going to happen, but this 3.7 feet, I believe, was this distance right here. We still need to add 10 to that, so this actually was 13.7 feet for x bar there. I'd like to say I didn't miss that, but I did. That's all right. So again, x bar for geometry 3, right? I'm pretty sure that was 3.7 feet, but we still needed to add the 10. So 13.7 feet times the area of the third geometry, 35.8 square feet. And there's the sum of x times area plus x times area plus x times area for each geometry. Now what we're going to do is just divide out the total area, which is the sum of all the numbers in this column, 16.25. I think I'll just write the units last. 24.4 plus 35.8, and those units are in square feet. I think what I'll do here is just pause the video to keep it from getting too long and calculate a value. Okay, I'm back, and I've got kind of a little toy calculator here, so I went ahead and did this piecewise where I just calculated this top part there, and I got 693. Summed these guys up, I got 76.45. Did the division, 9.06 feet. So that's putting that centroid x bar, somewhere right about here. Remember, from here to here was 10, so that looks pretty consistent with my picture here. So x bar for this geometry, I'll store this up here, 9.06 feet. And again, that's with respect to a coordinate system from the lower right corner, which I had already put in before starting this problem. Now what I'll do is we'll start working on y bar. need to make myself some space here. So, all right, to get y bar, again, what we're going to do is we're going to take the y coordinates of the centroids, multiply them by area. That's what gives them a weight. Divide out the total area. So y bar we're going to get by taking 2.17. And I'm going to go ahead and just put NCU here for note consistent units. That'll just make it a little quicker and easier for me. Times 16.25 plus 3.25 times 24.4 plus 2.17 times area 35.8. And again, these are all feet times square feet, feet times square feet, feet times square feet. So the whole thing in the top has units of cubic feet. I'll just put the units out there. And then we're going to divide that by the summed up area, which is 16.25 plus 24.4 plus 35.8. And I'll just put that in parentheses and put the units down here. That's in square feet. Like before, I'm going to pause this to keep this video a little shorter. Okay, folks, I'm back. So again, summing up all these values, I got 192 cubic feet. Summing up all these values, I got 76.45 square feet. Hopefully that's the same as what I got before. My memory's not so great. Do the division, comes out to be 2.5 feet. So it looks like the coordinates of the centroid, I've already written them over here, is about 9.06 feet to the right. So again, that's, maybe here. 2.5 feet up, maybe about there. That's just a guess, but so that looks like about where the coordinates of the centroid of this object is. So, is this the center of mass? Conceivably, yes. Is it the center of area? Yes. Right. What I've actually calculated was the center of area, and the reason it's a center of area is because I used areas for my weighting in the weighted average. However, if this is a nice uniform geometry, so if it has uniform thickness, like if I put a K or a Z-axis here, if it has a uniform dimension along the Z-axis, a uniform thickness, and it's made out of a uniform geometry, then the center of mass and the center of area would be in the same spot. So if that's true, we could then call this the center of mass. And if it's in a uniform gravitational field, we could also call this the center of gravity. So I hope this video helps demonstrate how to find the centroid or the center of area of a composite body. It's basically the same as my previous video where I talked about how to find the centroid for a function. It's just that you have a finite summation instead of an integration. I think these tables are of great value, and in some of my upcoming videos we're going to talk about how to find moment of inertias for geometry like this. So the tables will be extremely useful then. Hope this video helps. Have a great day.